What we basically have is we have a semi-batch operation in which we have some calcium chloride that is selectively absorbing water out of the air. And so we're removing water from a particular stream, and that stream has an unknown inlet molar flow rate, but the composition is known. It's 4.0 mole percent of water. Out of the system, we have an unknown flow rate, and we have an unknown composition, or mole fraction of water, so I'll call that XH2O. All right, and what we want to use is material balances in order to answer this problem. And the first part of the problem is, what is the value of N dot? Okay, and so we can do this, in the hint given in this problem, you can actually do this most easily by just doing a straight water balance. All right, and so the amount of water that's accumulated inside the system, inside the semi-batch operation, that's absorbed on this calcium chloride, we'll call NH2O, and that's equal to the amount that came in during the 5 hours, so 0.040 times N dot times 5 hours, right, minus the total amount that came out. Right, but you're given in this problem statement that 25% of what came in didn't come out, and so therefore 75% of the water that went in did come out. And so if we can just take this 75% number and multiply it by the number that's to the left of this. So 75% of what comes in comes out. Close a bracket there. All right, now we just need to know how many moles of water we have that are being absorbed by the calcium chloride. And so we're given that there's a gain in mass of from 60 grams, to 78 grams, so a gain of 18 grams. And so 18 grams of water. We just need to convert to moles, but it so happens that 18 grams is equal to 1 mole, and so we've accumulated 1 mole here. And then that's equal to our term on the right, and so we can go through and solve for N dot, and that's fairly simple algebra, and what we should get is that the total molar flow rate through the system is 20 moles per hour, okay, which is choice D. Okay, now let's go on to the next part of this problem, and I'll put that up here. It's basically the same problem with the same flow diagram, but now we're asking what is the mole fraction of water in the outlet stream. And to do this, we'll need to do 2 mole balances. We'll need both an overall balance and a water balance. And so let's start with the overall, which includes basically the air plus the water. All right, so our overall balance, again, our accumulation term is equal to the number of moles of water, because water is the only thing accumulating in the system. And this is equal to the total molar flow rate in over the time in which it occurs. So that is 20 moles per hour, as we just solved for, that's coming into the system. And the accumulation is over a period of 5.0 hours. All right, so we have a total of 100 moles coming in over that 5 hours then. Okay, we can then subtract from that our unknown number of moles or rate of moles per hour coming out times again 5.0 hours. All right, now we know again that N of H2O is 1 mole. That's how much accumulated. And so our only unknown is N dot out. And N dot out, we solve for that, it turns out to be equal to 99 over 5, which is 19.8 moles per hour. All right, so we lose 0.2 moles per hour, so over 5 hours we lose a total of a mole, which makes sense. Right, then we have 1 mole of water that's accumulating over this period. Okay, now the last thing we need to do is our water balance, and we're going to write that a different way this time than last time. Right, but our water balance, we can write that 1 mole of water that is accumulated is equal to 0.04, which is our percentage of our molar percentage of water in the inlet stream, times 20 moles per hour over the 5 hours of accumulation time. And then for our outlet term, we have our unknown mole fraction of water, X, and I think I called that XH2O on the previous slide. And we know that the total molar flow rate is 9.8 moles per hour, and again, accumulates over 5 hours. And now again we have a single unknown, XH2O, and so we can solve this problem easily enough, and we determine that it's 3.0%. And so that's answer B. And really we could have come to this conclusion without going through the detailed balance, because we know that we're only losing a very small amount of our total stream, since it's a dilute stream with water. And so we're going only from 20 moles per hour to 19.8 moles per hour as we go from the inlet to outlet. I know we also know that we're losing 25% of our water. Right? And so if the total flow rate is barely changing, and we can essentially neglect how much it's changing, and we're losing 25% of our water, that means we should go from 4 parts in 100 to roughly 3 parts in 100, with that 100 again being roughly constant. We see it goes from 100 to 99 here. And so this answer, which we get mathematically, is also an answer that just makes sense intuitively when we look at these numbers, and so you could actually come up with this solution in class without going through the details of the calculation.